Greetings. This is the sixth lesson in a series of short lessons on basics of power systems engineering. Network theory includes several important theorems or laws. One of these is the Norton theorem, which is covered in this lesson. This theorem is named after Edward Norton, the electrical engineer who discovered it. Norton's theorem states that any linear electrical network or circuit containing only voltage sources, current sources, and impedances can be replaced at any given terminal AB of the circuit by an equivalent circuit that consists of a current source in parallel connection with an impedance. The current source is designated as I sub NO, and the shunt admittance is designated as Z sub NO. The subscript NO stands for Norton. This theorem allows replacing any linear circuit with a single current source in parallel with an impedance. In this lesson, which serves to introduce this theorem, I limit the discussion to resistance circuits or resistive circuits. Since we are working with resistive circuits, I will change the notation from ZNO to RNO. The application of this theorem to AC impedance circuits is straightforward and will be covered in a future lesson. There are three steps involved in finding the Norton equivalent of any circuit. In the first step, we will short out terminal A to terminal B and calculate the short circuit current that flows from A to B. We'll call this current I sub NO. In the second step, we'll zero out independent sources in the circuit and calculate the equivalent resistance seen from the terminal AB. We'll call this resistance R sub NO. In the last step, a resistance of size RNO is placed in parallel with a current source of size INO to form the Norton equivalent circuit. I should mention that to zero out a voltage source, we replace it with a short circuit, and to zero out a current source, we'll remove that source, leaving an open circuit in its place. We're asked in this example to find the Norton equivalent of the circuit shown here as viewed from port AB, looking into this circuit. To find the I sub NO, we need to connect point A to point B and calculate the short circuit current that flows from A to B. The equivalent resistance seen by the voltage source consists of the 2 ohm resistor in series with the combination of the parallel pairs of resistors of 10 and 25 ohms, seen here. This combination evaluates to 9.143 ohms, the combination of 10 and 25 in parallel plus 2 in series. You see the calculation here, 2 plus the parallel combination of these two resistors, 9.143 ohms. The current I is found using Ohm's law, dividing the voltage over the equivalent resistance at 9.143, and that current is found to be 10.94 amps. We'll use the current divider to find the current that goes through the 25 ohm resistor, which would be the same current that flows from A to B, and that would be our I sub NO current that we're looking for. If you're not familiar with the current divider, I'll go quickly through it. If you have a current coming through and it's divided into two branches, one with resistance R1, the other one with resistance R2. The current that goes through one of these, for example, through R1, we'll call that I1, equals I times the resistance in the other branch, R2, over the sum of the two resistances, R1 plus R2. Using that principle here, you see that the current flowing in this branch equals 3.125 amps. Again, the main current, 10.94 amps, is multiplied by 10 over sum of the 10 and 25, resulting in this current. So we have found IAB, which we'll rename to INO. We'll next remove the wire, this wire here, and we'll look at and also at the same time we'll zero out the voltage source, and we'll look into the circuit to find the equivalent resistance of the circuit. You see that figure here, the short from AB is removed and the voltage source is replaced with a short circuit. The equivalent resistance seen from port AB comes to 26.65 ohms. Again, to find that, we take the parallel combination of 10 and 2, shown here, and then add the 25 ohm to it, because they'll fall in series. The Norton equivalent circuit is then formed by replacing placing the RNO in parallel with the current source INO. Notice I have changed the designations from IAB to INO and R equivalent to RNO. Here is the Norton equivalent circuit. A current source of 3.125 amps in parallel with a shunt resistor of 26.67 ohms. I'll take a short break here for an introduction before continuing the lesson with another example. My name is Fuad Albandi. I am a PE in electrical engineering in the state of Maryland. This is the 5th lesson in a series of lessons on basics of electrical power engineering. It's actually the 6th lesson that I have published on YouTube. You'll find my name and email on this page. You can visit my website at the link on this page, own-your-destiny.mylearnedworlds.com, and you'll see comprehensive modules on important topics in power systems engineering on my website. I will now continue the lesson with example 2. In this example, we are asked to find the current through the 10 ohm resistor using Norton's theorem. To do this, I'll remove the 10 ohm resistor from the circuit, find the Norton equivalent of the remaining circuit, and we'll replace the 10 ohm resistor back in the equivalent circuit that I find, and from that I'll find the required current. Just as in the previous example, we'll short out A to B to find the short circuit current INO. To find the current from A to B, I'll first calculate the current I that's supplied by a 120 volt source. And to do this, I'll need to calculate the equivalent resistance seen by the source looking into the circuit from here. Starting from the right hand side of the circuit, we have these two resistors in parallel, and the result is then in series with the 5 ohm. then the total calculated here is in parallel with the 20 ohm, and that result is in series with the 3 ohm. So the calculation is, which is seen here, follows that logic. 8 and 25 in parallel plus 5, the result in parallel with the 20 and then added to 3. The current, well, the answer comes to 10.12 ohms. The current is found by dividing the 120 volts by this resistance, and it comes to 11.86 amps going through here. 11.86 amps. This current is then divided between the 20 ohm resistor and the other branch that's in this circle here. The circled branch has an equivalent resistance of 11.06, and I need the current through the 5 ohm resistor, which can be found through the use of the current divider again. So we have 11.86 coming through here. There's a branching of this current. One of the branches has a 20 ohm resistor, the other branch has 11.06 ohm resistance. So the current that goes through the 5 ohm resistor is 11.86 times 20 over sum of 20 and 11.06, which is shown here in the denominator. And that comes to 7.634. That would be I1 going through the 5 ohm resistor, 7.634 amps. This current coming to this junction is further subdivided between the 25 ohm and 8 ohm resistor. We're interested in the current that goes through the 8 ohm resistor, so again we use the current divider once more and take the 7.634 current coming in here, multiply it by 25 over sum of the 8 and the 25, and the current through 8 ohm resistor, which also flows from A to B, is 5.783 amps. Well, that's the INO that we were looking for. After that, we'll remove the short and we'll replace the voltage source with a short circuit to zero it out and look into the circuit to find the R equivalent, which is our RNO. So again, to find the resistance working from a far end of the circuit, 3 and 20 are in parallel, the result in series with 5. The result so far is in parallel with 25, and after that, that result is in series with 8, and I show that in this formula. 3 and 20 in parallel plus 5 in series, total parallel with 25, and added to 8, which is in series. The total resistance looking into the circuit from AB is 13.83. We'll rename the IAB that was found a few slides back. We'll rename it as INO, and we'll rename REQ as RNO and form the Norton equivalent circuit, which you see on the next slide. Here we have a current source of 5.783 amps with a shunt resistance of 13.83 ohms. To find the current through the 10 ohm resistor, I'll replace it back in the circuit between points A and B, and using the current divider we'll find the current that flows through it. Here's the 10 ohm resistor replaced between A and B, and because we're interested in current in this circuit, in this branch, 10 ohm branch, we'll take the main current coming through to this junction, multiply it by the resistance of the other branch, 13.83, divided by the sum of the two. And the current is found as 3.356 amps. The circuit in this example contains a current source of 15 amps instead of the voltage source of the previous example. The rest of the circuit is the same. Once again, let's remove the 10 ohm resistor from the circuit and short the terminals A to B. "15 amp is flowing in the 3 ohm resistor here. We can find the current through the 5 ohm resistor with use of current divider again. So we're interested in I1. I1 is calculated. Well, first of all, we need to calculate the total resistance of the cluster of resistances in the circuit. And so that comes to 11.06 ohms. Then we use the current divider to find I1 from the 15 amp flowing into this junction. And that comes to 9.659. To find the current through the 8 ohm resistor, we use the current divider again by multiplying the current through here, 9.659 times 25 over 25 plus 8, and that will give us the INO as 7.317 amps. We'll now zero out the current source by removing it, and we'll remove as well this short and look into this circuit to find the equivalent Norton resistance. Here you can see that the current source was removed, leaving an open here in this place. And looking into the circuit from AB, we can calculate RNO as 5 plus 20 in parallel with 25 plus 8. Notice that this resistance, 3 ohm resistor here, does not come into the picture for this calculation. And the REQ ends up at 20.5 ohms. Looking in, we replace, first of all, we form the Norton equivalent from this current source and this shunt resistor. And now we can place back the 10 ohm resistor between A and B and calculate the current through it. Here it is. The INO is calculated as was calculated earlier. The RNO is in place, and the 10 ohm resistor is placed back between A and B. 7.317 coming to this branch, subdivided between these two resistors, and we're looking for current through here. And that's calculated as 4.918 is the current that the example was looking for. We have reached the end of lesson 6. This is Fuad Al-Bandi, founder of the educational group Own Your Destiny. If you enjoy watching my channel, please click on the subscribe button. You can also visit my website at the link shown on this page. Email me with any questions or suggestions. And thanks for watching this presentation. I hope to see you in a future lesson.